So in the last unit, we talked a little bit about these equations and solving equations, looking at things like this. And remember, the key was to look at the equation and figure out how it was built or how it was put together, and then use that to take it apart. So when we saw an equation like this, what did we have to do to take it apart? We have to add 2. That would be the last piece put on, was subtracting 2. Now we have to add 2 to remove that piece. So 58 plus 2 is 60. Adding 2 here just removes the subtracting 2 to leave us with 5x. The next step would be dividing by 5. Good. So x equals 12. And we always could go back and double check by replacing the variable with that number. So instead of 5x, it could be 5 times 12 minus 2. And hopefully that'll equal 58. 5 times 12 is 60. Minus 2 is 58. So it does check out. We get the same value on each side of the equation. Well, today we're going to look at some applications of these equations and where they come from. To do that, we're going to look at some geometry and geometric formulas and things like that. We're going to start out talking about some basic concepts in geometry. And in geometry, the most basic concept we have, the most basic item we have in geometry is that right there. Looks like a dot. Geometrically, it is called a point. It is simply a location. It has no dimensions, no length, width, or height. It is just a location. All of our items in geometry are constructed from that point. If I take a point and I pull it in a single direction and stop, what I've created, some people would call that a line. It's actually a line segment. A true line would go on forever in both directions. So that's called a segment, a line segment, because it's a portion or a segment of a full line. And in most practical geometry, that's what we're using rather than full lines themselves. So that segment there was created by moving that point in a single direction. The distance we moved it is defined to be the length of that segment. And most dimensions in geometry actually start out that way, as a moving distance that becomes a length or a width or some other dimension. Now, another concept that's not too hard to grasp, the whole idea of a line going on forever in both directions is kind of difficult, because I can picture it going on forever in one direction, but it has to start somewhere, right? So to me, a little bit easier concept to grasp is this here. Just what I described. A point starts in one spot, and then we take it and we just keep going forever in one direction. That is what is called a ray. Kind of like a ray of light from the sun. It starts at the sun and just goes on forever. Well, if we come back to that starting point, and now we take that point and we move it in a different direction, creating a second ray, we have also created, with the combination of the two rays, a geometric item called an angle. So the two rays make up the sides of the angle. And that common starting point that started both rays is referred to as the vertex. Now, the size of an angle, the definition of a size of an angle has changed over the years. Originally, the angle was defined as a difference in direction. It come from back when navigation was used pretty heavily, and most people had some idea of navigation. If you look at a map, straight east was defined to be 0 degrees. Then north was 90 degrees. West was 180 degrees. South was 270 degrees. And then 360 degrees brought you back to east, so you started over at 0 again. And an angle was defined as a difference in direction. So let's say we had a ray that pointed off in this direction. Let's say that's at 26 degrees. And another ray that pointed off in this direction, let's call that 74 degrees. The angle between those two rays was defined in the difference between those directions. So 74 minus 26 is 48 degrees. So this angle was defined to be 48 degrees, the difference in their directions. That is the original and probably most technical definition of an angle. Now, in recent times, since navigation is not such a big thing, the average person doesn't know a whole lot about navigation anymore. They've altered that definition a little bit to where we use benchmarks. If we make a complete circle, that is, of course, 360 degrees. Sure. Back up here?
Yeah, right.
Okay. So a complete circle is 360 degrees. And of course, then there's the benchmarks. The half circle is 180 and so on.
Okay.
So angles have come to be defined as a fraction of a complete turn. This angle right here is defined to be 45 degrees, for example, because that angle is 45 3/60ths of a complete turn, a complete circle. That one's a little bit fuzzier definition to me, but it's kind of the new definition because navigation, again, and directional angles and stuff is not as commonly known anymore. Oh, yeah. So again, we have some benchmarks. If I have an angle, if I have a ray that starts out in one direction and I turn back to that starting point and I go in the complete opposite direction, how many degrees is that angle? 180. Half of the 360. It's half of a complete turn, or half of a complete circle. If I make a turn and I start out and I make a square corner, or what's called a right angle, that is how many degrees? 90 degrees. Makes a square corner, or a right angle. Those two angles, the 180 degrees and the 90 degrees, happen often enough, and they're used enough in application where there are special names dealing with those angles. If I have two angles that add up to 180 degrees, like these two angles here, I have this angle and then this one here, combined to make a straight line or add up to 180 degrees. Those two angles are said to be supplementary. Or supplements of each other. If this angle here happened to be 53 degrees, this angle over here has to be 180 minus 53, or 127 degrees, because they must add up to 180 degrees in a straight line. If I have two angles that add up to make a square corner, or a right angle, they're called complementary. Let's say that this angle here is 68 degrees. This one up here is going to be 90 minus 68, or 22 degrees. They have to add up to 90 degrees. They're called complements. Now, if you're anything like I was when I first learned these, I could remember the words supplementary and complementary, but it took me a while to remember which one was which. The thing I use to remember them is this. 90 degrees is a right angle. I'll give you complements when you are right. So complementary adds up to a right angle. So if I ask you for the supplement of 148 degrees, how do I find that? Perfect. 180 minus 48 is 32 degrees.
So anytime you see the word supplement, it has to be equal
180, exactly. I ask you for the complement of 13 degrees, how do we find that?
What did you say? Oh.
There we go. The complement of 13 degrees is 90 minus 13, or 77 degrees. Now there are some other relationships we run into in our angles. I'm dealing with our, I think we could have some line segments that intersect. Like this. And there are some very special relationships here. For example, if I tell you that this angle here is 31 degrees, I now know every other angle here because there are 4 pairs of supplementary angles. Remember, supplementary is 180 degrees, so that means anything that creates, any 2 angles that create a straight line are supplementary. So this is a straight line here. That tells me that this 31 degrees and this angle must add up to 180. They're supplementary. So 180 minus 31 is 149 degrees. It's 180 minus the 31.
No, but why was that again?
Why is that? Because
Exactly.
this is a straight line.
It's because it's a straight line.
Because that's a straight line, and those 2 angles add up to the straight line. They have to be supplementary.
Okay.
Because the straight line is 180 degrees. So anytime you have 2 angles that add up to a straight line, they're supplements. You look confused back there, Billy.
Why does that? Why those 2 lines have to act? What if that line was shorter than
The lines, not the lines, it's the angles, remember. It's the fact that this angle here and this angle here combine to make a straight line. If you ignore everything else in the picture, it would look like this, right? I'm just taking out this little piece here and ignoring it for a second. This angle and this angle add up to a straight line. So they have to be supplements. Now, there's also a straight line going this direction, which means this angle here and this angle here must also add up to a straight line, or add up to 180. That makes this 31 degrees, because 180 minus 149 is 31. Anybody want to guess what this one down here has to be? 149. Because those 2 add up to a straight line as well. When you have 2 intersecting lines, like I said, you end up with 4 pairs of supplementary angles because you have straight lines going in every direction. So when 2 lines intersect, there are only 2 angles that are formed. There are 4 angles that are formed, but only 2 unique angles that are formed. These 2 have to be the same, and these 2 have to be the same as each other. So if I give you these 2 lines and I tell you that this here is 81 degrees, what's this one have to be? 81 degrees. Perfect. What's that one have to be? 180 minus 81 would give you 99 degrees. Okay, now we can do some problem solving with that. For example,
The 2 were 81. What was the other?
99.
91?
Yeah.
Doesn't matter how long
Doesn't matter how long
that line
the line is, it's the angles.
Right.
Yeah.
Okay. Gotcha.
Let's look at this. I want to know how big each of these angles are. Well, I just label them as 3x and 9x. Is that enough information to figure out how big they are? Well, it is. because I know that those two angles have to add up to 180. They're supplementary. They make a straight line across here. So I know that the 3x angle plus the 9x angle has to add up to 180. So now I have 3x plus 9x, which makes 12x equals 180. Then what? Divide by 12. Okay. So x equals 15. All done, right? We got x. No, we have to answer the question. What was the question to find x?
Yes.
Part of it, the question was, how big is each angle? Once we know x, this angle is 3 times x, or 3 times 15, which is 45 degrees. This angle is 9 times x, that becomes 9 times 15, or 135 degrees. Now we're done. Now we have actually answered the question.
Why was I thinking you have to take 12 away from 90? You know what I was lying?
Well, because you were thinking it was added. It's 12 is put on. The 12 has been combined with the x by multiplication, so to get rid of it, you got to divide. If that was x plus 12, then you would subtract 12.
Right, okay.
Yeah.
So then to find the other side, then you would take 180 minus 45, and then 180 minus 45.
Yep.
Okay.
Or you know at this point, you know that this angle here and this angle have to be the same. And you know this one and this one have to be the same. So once you have two of them, the other two just kind of fall into place.
Then where would 180 come in?
Well, 180 comes into play because these two do have to add up to 180. Yeah. Yep, that would be one way to check it. Oh, let's see here. Let's find those two angles. Anytime you see this little square box down here in an angle, that means it's a right angle.
Oh, is there such a thing as a left angle?
No.
Okay. Well, why is there an next one?
Oh, yeah, that's a good question. Where does the term right come from? It comes from construction and building. A corner is right if it's square. Bless you. Because it was called a square corner. But that corner is right. It's correct. Because
Okay.
it's not right or left as in right hand or left hand. It's right as in correct.
Oh.
So a correct corner is square. So that's a right. That's the correct angle or right angle. Yes, Cody.
Could you just look it over? Then it would be going the other way.
It's still a right angle.
Oh, yes, but still, just to prove the point.
Not sure what the point would be, but it's still a right angle because it's still a square corner.
Well, yeah,
Because I don't even know what a left angle would be.
as you're just a point there.
Yeah, because like I said, it's not right and left as in right hand and left hand. It's right as in correct. So anyway, what's the relationship between these two angles here? Between,
They have to equal 90.
yeah, they're complements. They have to add up to 90 degrees. So 4x plus x equals 90 degrees. Now, as Cody said, the first thing we're going to have to do here is combine the x's. It's easiest if you think of this as 1x. Think of like 4 inches plus an inch is 5 inches. 4x plus x is 5x. Now what would we do? Divide by 5. Okay, so x equals 18. Now what? Okay, so this one's easy. This angle is just x, so that is 18 degrees. This angle up here is 4 times x, so 4 times 18 is 72. So that is 72 degrees. Yeah, that is one way. You should always double check these. Since they're supposed to add up to a right angle, add up to 90, do 72 and 18 add up to 90? Yeah, they do. So If they don't, you know you did something wrong. If they do, it doesn't necessarily mean you did it right. It just means you didn't make a really bad mistake. Looking at this here, there is a relationship between these two angles. Here, I'm going to change this a little bit. I don't want to record that big. It should be a 19 here, not a 29. What is the relationship between those two angles? From what we've seen so far, we know they have to be the same. They have to be equal to each other because of where they're at. There is a special name for that. They're called vertical angles. When two lines intersect, we talked about how the fact that they form 4 pairs of supplementary angles, or 4 pairs of angles that add up to 180. Well, they also form pairs of vertical angles. The angles that are on the opposite sides of the intersecting lines have to be the same. So we know in this case that 2x plus 13 has to equal 3x minus 19. And now we have to solve. What are we going to have to do with that? Get rid of one of the x's. Which one are we going to get rid of? Which, well, if they're on the same side, we would combine them and add them together. But they're not. They're on opposite sides of the equal sign, so we can't combine them together.
So do we take the 2 away and make it 3?
There you go. We get rid of the smaller one, which is the 2x. So it's gone. Leaves us with 13. And we have to take 2x from the other side. So 3x take away 2x is 1x or just x. If you wrote 1x, it wouldn't be wrong. It's just simpler to write it as just x. So now to solve this, we have to add 19, which gives us 32 equals x. Now, of course, we're not done. We need to, we need to go back up here and put 32 in for x to figure out what the angles are. So this is 2 times 32 plus 13. 2 times 32 is 64, plus 13 is 77 degrees. Now we want to double check over here, make sure we get the same number. 3 times x will become 3 times 32 minus 19. 3 times 32 is 96. Times, yeah. So 96 minus 19 is 77 degrees. So we get the same answer. So that tells us there's a good chance we're correct there. There are all sorts of other geometric relationships that fall into this. We've talked about perimeters already. The perimeter of a rectangle. We've talked about length plus width plus length plus width. We're going to shorten that up a little bit. It is 2 times the length plus 2 times the width. If I tell you, now last time I gave you either the length or the width and then the perimeter, and we solved it from there. This time we're going to look at a little bit more complex example. Now we're going to say the, oops, not perimeter, come on. The length of a rectangle is 3 times the width. If the perimeter is 176, find the length and the width. I draw out my rectangle. I got the length and the width. One of those two, either the length or the width, I have to have more information about. Either I need to know the size of it, or I have to have some other expression to write it. If I look up here, it's this first line that tells me the length is 3 times the width, which means the length here is going to be 3 times the width, or 3W. That's 3 times whatever the width is. Does everybody see where the 3W came from? Because it says the length is 3 times the width. Now, I go to this formula here, and I'm going to replace it with information that I have. I know that P stands for perimeter, which is 176, equals 2 times L is going to become 2 times the length is 3W. Plus 2W. Do I have another way of writing W? No, it's just W for now. Now I solve that equation, I will find W, and then I can go from there. So what's the first thing I have to do here? Multiplying 2 times 3W is 6W. And then the plus 2W doesn't change. What would be next? Add. The 176 doesn't change. But we can add 6W and 2W makes 8W. And then divide by 8. 176 divided by 8 is 22 equals W. Good.
I didn't do it that way, but I did get it.
As long as you got it, that's what matters. So that means you can come up here, the width is 22. We need to find the length, which will be 3 times W. 3 times 22, or 66. And then we can go back and plug those in the formula if you wanted to and add them up and make sure that adds to 176 for the perimeter, and it will. But if you were doing this on your own, I would recommend you go double check that before you accept that as your final answer. In my math lab, by the way, be very careful, because it'll ask you, it'll give you the problem, and it'll ask you length equals whatever, or width equals whatever. Make sure you read it carefully. Most of the people that get these questions wrong in my math lab, it's because they put the width in where the length was supposed to be, or the other way around, and that's why it marked them wrong. Just make sure you read them carefully and take your time with them when you enter.
I can't remember which problem I was working on, but there was 2 squares.
Yep.
And in the second square, there was a drop down that said something like inches or inches squared.
Yep.
Well, I didn't know, like, if I was supposed to put a number in both of them, or if the second box.
Second one was just a pull down menu. Just put inches squared, feet squared, or inches. Yep.
Okay.
They're talking about areas in a question like that. Our formula for area of a rectangle, that's the length and the width. The area of that rectangle is the length times the width. So let's say that this has a width of 7 inches and a length of 15 inches. And it asks you for the area, where you're just going to plug the numbers in here. 15 inches times 7 inches, which is going to give you 105. 15 times 7 is 105. But when we multiply, remember, we also combine the names. Inches times inches will be inch squared. And that's what that pull-down menu is asking you to pull down. Is it just inches, or is it inches squared? So you'd have to make sure you pulled it down and selected inches squared. Well, that one's kind of a simple one. What if it were to ask the area of a rectangle is 39 inches squared. Find the length if the width is 3 inches. Area is length times width. We know that the area is 39. The length is what we're looking for. The width is 3. So put 3 in for W. How do we solve that equation? 5 by 3. 13 equals the length. So the length is 13 inches. You gotta make sure you put the units in. Now, what if you were to get a little bit, they might just give you a rectangle like we did and ask you to find the area. So let's say we have a rectangle like this that's 9 feet by 16 feet. How do I find its area? Well, we just saw it. The area is 16 feet times 9 feet. Should come out to be, what, 90, 54, 144. Remember, it is feet squared. What if it's not a simple rectangle? What if it looks like this and they want the area? What are we going to do here? Well, we only know how to find the area of rectangles right now, so we're going to have to chop this up into rectangles. I can do this. I can cut it right across there. This rectangle here now is 8 by 15, or 18 by 15, which is going to be 270 inches squared, or square inches. How about this rectangle up here? I know it's 6 inches here. What's this dimension? Where'd you get the 5? Perfect. Perfect. This is 15 here, which means this piece here has to be 15, right? Since we cut that in a rectangle, the sides, the ends are the same. So if this whole thing is 20, you subtract the 15, there's 5 left over. Very good. That's a concept, that idea of subtracting dimensions like that. A lot of people struggle with that. So it's good that you guys got that right away. So now that area is 6 by 15, or 6 by 5, I should say, which is 30 inches squared. Adds up to a total area of 300 inches squared, or square inches. What do you think? No, you can do it a lot easier. You're probably thinking doing this, making it a big one, and then subtracting it out. That's the other way you could approach that, is do a 20 by 18, which is 360. Then this is 5 by 12, which is 60, and subtract it out. Well, it depends on the problem. I could have a problem like this. It also depends on your visualization, but you could run into problems like this. Ask a question, I decide to do something that hurts you. Yeah, that's what I'm here for. So something like this. If I want to find the area of that, if I try to cut this into smaller rectangles, I'm going to have to do a lot of cutting. I'm going to do there, there, there. It's a lot of finding dimensions. It's going to be tough to do. This one, though, however, would be pretty simple to do if I made it a big rectangle and subtract it out. The big rectangle here would be 24 plus 4 makes 28. Going this way, 6 plus 5 makes 11. So that big rectangle is 28 by 11, or 308, whatever units it is. Square units, square inches, square feet, whatever units it is. But then I have to subtract out, this one here is 3 by 5. So minus 3 by 5 would be 15, so that's down to 293. This one here is 2 by, I need this dimension. If this is 28, I have 3 and 15, which would be a total of 18 to here. So this piece has to be 10 to add up to 28. So that's 2 by 10 to make that rectangle. That's 20. So you subtract that off to get 273. And then this one here is 4 by, can you tell me that one? I've got 2. And 7 puts me at 9 here. If it's 11 total, this one needs to be 2 as well. to add up to 11. A bit confused, Cody. You got that? Finding that missing dimension? That's the big thing I want to make sure everybody has, because that's the tough part for a lot of people. You know the whole thing's 11, so it has to be 11 from here down. You've got 7 and you got 2 here. So that's a total of 9 to that point, so you need 2 more to get up to 11. So now this is 4 by 2, which is 8. So 273 minus 8 is 265 square units of whatever those units were. What do you think? It take a while to get used to? There are some people that really struggle with the visual side. So if that's you, don't feel bad. You're not alone. There's a lot of people that do. Be patient with it. Keep working with it. Ask me questions. We'll teach you how to get through it. So here's a new homework. It is due for Wednesday. Many of you have already started it. New homework due Wednesday. No quiz yet. The quiz won't be assigned until Wednesday. Remember, tomorrow is career day, so you get a late day tomorrow.
So tomorrow you